was
All
not able
right.
to do that because of a power outage.
Okay.
So we will start.
Thank
Please
you.
let's pray. Father, we
All
thank you
right.
for this other opportunity that you gave us this morning to get together again and learn. Father, we ask that your spirit, let your spirit comment back this meeting up and show us the way.
Amen.
Let your spirit guide us and be with us from the beginning until we will put an end to this meeting. For in Jesus' name
Amen.
we pray. Amen. So yesterday, what we did yesterday is to establish, well, we have not totally established it yet, but we have at least started um, finding the target for our ailment of interest, which is breast cancer in our case, from two different databases, the Cancer Genome Atlas TCGA and the Gene Expression Omnibus. So we were able to finish up with the TCGA and we were working on the Gene Expression Omnibus. So we were able to download, uh, how do you call it? We were able to download the the database the data sets from the GEO, but we were we are yet to arrange and just consider the genes of interest. Please, can you remember why we need to, I mean, um, what I've just said? Can you remember why we need to do that?
Why we need to select the genes
Thank you.
from
So I think that's
the
the expression, select the genes. Yeah.
yes.
So why
Okay.
do we need?
I think yesterday you said we needed to narrow it down. That all the data that was collected from the um GEO, the gene expression omnibus, was not.
Yes.
I think the p value that they gave us was not narrowed down. So we were supposed to select a p value of two or so that we will have more accurate results from the database, something like that.
Mm, yeah. So there is a cutoff or there are cutoffs that we need to set. The log FC, the fold change that we say for in our case we want to set it to 2, absolute value of 2, and the p-value should be we want to set the p-value to 0.05. So because of the with the GEO data set or database, we didn't do that immediately in the online in the database, in contrary to the TCGA where we were able to on the Gapia database, we were able to do it directly. Okay, you are correct. Thank you. Uh, so we will start from there. We will try and arrange it in the Excel file. Yeah. Okay, let me send the Excel file, share the Excel file. I think this is the Excel file. I hope you can see the Excel file.
Yes, sir, we can.
All right, so the first thing we want to do is to consider the p-value and fish out uh, whatever is not consistent with our cutoff of 0.05. Let me try and put this in as a table. In fact, I can delete this one for now. I don't need it. Okay. we have our log FC, and then we have the p-value here. So okay, now let me put this as a table. What I'm trying to do is to insert a table with this data and make it easier for me to arrange the p-value so that I can delete easily what I need to delete. I could do this beforehand, but I'm afraid that it will not help you people uh, to follow. This will take them. Let me just do it like this. Insert, insert the table. What's going on here? Um, my screen is frozen, but I hope that it will come back very soon. Let me just try this one. Mhm. Okay, now let me insert the table. The version about large numbers and take significant amount of time. Yeah, that's the problem. So, so for today, we want to I'm hoping that we can be able to finalize the establishment of our AIMET breast cancers data sets, and then find out a plan that we want to work with, and then go in the database, corresponding database, and uh, fish out the different components of the plants in the database. Actually, generally, what I do is plus the database, I will also need to go and check quest the literature. Yeah, so I usually go on PubMed also and find out related publications about the plant, and find out the components of the plant according to literature, and then add it with what I can find in the database that is already available, uh, that I will use. So that will actually help me to make sure that I do not leave any component unknowingly. At least it's minimize the risk of leaving the leaving out some components. So we hope that we can reach that today, and by the moment we find out the component, we will then be able to uh, go and find out the different targets that those components that are predicted for those components. Okay, so if we come back to this one now, I hope you are still, I guess you are still seeing my screen. Now we have now created the table, and what we want to do now is to arrange, to sort the p-value and the log fc um, from let's say from the smallest to the largest. That will help us to easily delete everything that every genes that is not showing a significant um, p-value. Let me put this in tests. For me, it's easier to see. So I hope you can see the p-values in the B column here. So I just clicked on the tab there, and I arranged and sorted the p-value column according to the smallest to the largest. That will actually help me to delete easily every genes that is not compliant with the p-value of less than 0.05. So manually, I will just be scrolling down until I get to the point where, okay, yes. So until I get to where uh, is more than 0.05. So I will just be scrolling down because I already sort it out. So there's no danger in just scrolling down until I find uh, where the unnecessary genes are. So till now, we are still under p-value of less than 0.05. Okay, then okay, so from okay, so from this number 28 34, we already have a p-value. We start having a p-value of 0.05, which is not what we want. So from here until the end of this table, we will delete everything. So I will just now come down. By the moment I selected that row, the first row of undesirable gene. So yeah, from here now I can just scroll down till the end, and with shift click, and the rest is selected, and I will just click on delete, and it will delete the rest. So from this point 2833 until the the first row, we have genes that are significantly either upregulated or downregulated, so highly expressed or underexpressed. Now, what's the next thing to do now is uh, to sort out the value of the log FC, the fold change. So we want to, here also, we want to sort it from the smallest to the largest. And what we want to do here is, okay, so when me I'm working, I also consider the genes that are underexpressed. So the genes that are underexpressed compared to the normal one, we the value of the FC um, will be in negative values, and the genes that are highly expressed, the value will be in positive, with a positive sign. So, but I noticed that some people just consider the genes with the genes that are highly expressed compared to the normal one. And I believe that the idea behind that is that the compound that they want to study, they are studying it with the idea that the compound can be an inhibitor. So they instead want to one compound that can inhibit particular genes, or the genes that are overexpressed. I believe that's why they just consider the genes that are highly expressed. For me, I believe that sometimes compounds work not only by acting as inhibitors, but they can also act as activators. So suppose there is a gene that in a normal samples, in a normal tissues, the D is highly expressed. That means that's how the genes is supposed to be normally, and there will be no involvement in disease. But by the moment that genes that normally is highly expressed start being underexpressed, that means that and that's where is being involved in the occurrence and even progression of the disease. That means that there is a problem with that genes, and the problem with the genes making it being underexpressed is leading, or is initiating, or either participating in the progression of the disease. So if we can act on that particular genes, I believe that it is for us to find a compound that we actually activate the gene instead. Yeah, so because there is this thing that we call a that is called a how do you call it? Tumor suppressor genes, for example. So tumor suppressor genes, for example, in general, tumor suppressor genes, you will find out that generally they will be downregulated in cancer, for example. Yeah, so in cancer, so what we want to do if we are applying or if we are using a drug, we obviously want to actually increase the expression of that genes, because as his name is saying, it is a suppressor of tumor. So we want to increase the expression of that genes instead. So we want to find out a compound that will actually activate uh, the whole machinery of having the being expressed. So that's why when I'm working when I'm fishing out the targets, I don't disqualify the under expressed one. I also consider the under expressed ones, because just like I hope you understand, because of the how do you call it, the explanation as I've just given. So coming back to our table, now what we want to do is we said that our cutoff here is 2. Our cutoff here is 2, and we were saying that absolute value of 2. So that means what is after 2? Values after no, not after. Values before 2, we are not interested in that. But from 2 until plus infinite positive, we are interested in that. And at the same time, we are interested in genes that from the value of FC -2 until minus coming down. I get, I hope you are getting what I'm trying to say. Yeah, someone wants to say something.
Yes, sir. I understand what you're saying.
Oh,
I
okay, thank you.
understand. I don't know about others though.
I'm sure they understand. I'm trying to say if there's a way I can draw something here. Um, are you seeing my screen? Please, can you see this PowerPoint slide?
Yep, yep.
Okay. So
Yeah.
what I was trying to to explain is that so what I was trying to explain is this. If we have Okay, so if we have this, for example, let's say we have a -2 here and we have 2 here. So the full change range that we are interested in is from 2 here till positive infinite, and from -2 here till negative infinite. That's the range in which we are interested in. Do you get it now? I guess you get it. Okay, so that's actually what we will be doing on that table. So we have the value of uh, smallest to the largest. So from -1 till we find -2, we will delete. Yeah. Parce que lui, il a dit. Noir, 1, 2. So in this particular set of this thing, let's go to yeah. Okay, so if we are considering our cutoff of absolute 2, the genes that will be remaining for us, considering the set, considering the uh, considering this data set will not be enough. It will be very few, because I hope you are understanding what I'm saying, because we will have to delete since I chose the first row that I chose, even until this place, and it will just be remaining 3 here. That's actually also why, let me talk about this immediately. So when you are doing when you are conducting your study, you are not that's also why you are not using just one data set. For example, for the GEO, I used, for example, I used like I used 4 data sets when I was doing my work. So I used 4 GEO data sets. It will give you a range of a large range, yeah, of the genes that you will actually be using. But for the purpose of this discussion, we will just stick to that and use those three genes. Yeah, let's do it like that for understanding for now. But when we need more genes, I will just bring in the other data set that I had already, and we will continue with the following steps. So, so what we do is, by the moment we find out, we fish out according to p-value. Now we are fishing out according to the FC. So what we do is we delete everything that is not actually um, relevant with our cutoff. So if we follow our cutoff of 2, absolute 2, these are just the three genes that are remaining actually. So, like I said, I will just add other data sets, and with other data sets, combine them together, we will have more genes. Now, what you can also do is, as I said yesterday, some people, in fact, in the literature, some people even use a cutoff of for the FC, they use a cutoff of 0.5. Some people use 1.5. So you can define your own cutoff according to what you want, if I can say it that way. So this is how you sort out the genes in Excel after downloading from GEO. So after these steps now, because we are using two data sets, we will find we put we will select these genes that we have here. We will select them and add them together with the genes that we had from the TCGA database to make up our own database of the breast cancer that we want to use for our study. So that's how it actually works. We will end this one here, and we come right back. Yeah, we come right back in less than 1 minute. We will just come back right now. Thank you. Welcome back, Dr. Kaitano.
Thank you, sir. Thank you, sir. Honorable Doctor.
Oh, man. Hello, Jacob. Please, are you seeing my screen?
Nope, nope. There's this. I think it's a Zoom screen, right?
Okay, you are seeing the Zoom screen. What
Yeah, and
about now?
I can see the mouse. I can see the desktop. You are showing the display of desktop.
Okay, can you see PDF now?
Yep, yep. You are
Okay,
scrolling up and down.
all right. That's what I wanted. That's okay. Fine, thank you.
Welcome, sir.
Yeah, so I guess now you are seeing an Excel file.
Yeah, sure.
Okay, that's good. So we will continue. So like I said before, we will now put together the TCGA and the GEO genes that we fished out. We will now go to our folder, and let's open the TCGA with Excel. Okay, so this is TCGA data set. What we first want to do now is to bring in the genes that we find. Okay, well, to bring the genes in the two data sets, or if you use more than two, all the data sets, you bring them together, and by using Excel, you will remove the duplicates, because there are some genes that appeared in the TCGA that can eventually still appear in GEO. So you want to you want to remove the duplicates. By removing the duplicates, it just means that if the genes here, these genes here, AASS is from TCGA, if it appears in the GEO data sets, so you want to have in your data set, your established database that you want to use for your study, for your work. You want to have only one AASS. You don't want to have AASS, and then after, when you will be scrolling down, or you have again AASS. So that's what we will just be doing here. uh so I will just copy the genes that I have here, these three genes, because it's three is easier here. But even if it was a lot of genes, you can just select the whole column and copy the genes that you are interested in, and you go on the other one, and I will just paste under the and I will just paste it here. So now I have my genes, the whole genes for the data sets that I'm interested in. If we like, uh we can create another Excel sheet and just put those genes there. But I'm not interested in these ones now. I will just delete them. I hope you are following me and you are understanding. So now we have our database of the breast cancer, of the genes of interest, based on the different cutoffs that we set, and for our study. I can actually uh, save this one. So I can just set it like breast cancer database for my own work. So we have now successfully established uh, established the target database of the breast cancer. That was the number one thing we wanted to do. So the second one now is to establish components database for our chosen plant. If you remember yesterday, I said that I've not chosen any plants yet. So I don't know if someone is interested in proposing a plant for us, the person can do it as quickly as possible. Otherwise, in the next 1 minute, I will find a plant and we can go on with the plant. Someone proposed a plant. So I also wanted to say that if you remember in the beginning yesterday, okay, except if you didn't join. Yeah.
Makalanga Batera.
Sorry, can you write it for me? Is it possible in the chat? Okay, received. All right, Macaranga bacteria. So I was saying that if you remember yesterday in the beginning, except if you joined late, I was saying that in the network pharmacology is either you have a formulation. So that's what the Chinese do most of the time. Them, they have formulations that they are already using in their country for treatment. So and then they are interested in the mechanism behind the work, the effect of the formulation. So the formulation has a name, a particular name, but we know that formulation is, composed of different plants. So they have their own database. The Chinese have the database for those formulations, those medicines that they have. So each formulation has a set of plants that are incorporated in that formulation that are put together to make the medicine. So when them they will be doing the network pharmacology to elucidate the mechanism behind the effect of their formulation. That means primarily they want to know or they find out the plants that are inside those formulations first. And then the different, all those plants, they will now use, they will not take those plants and then find out the components or in individual and each plant. So it's from there finding out the components that they will now go and look for the uh, the targets, the predict the targets using the different databases. And but other people that don't that one is when you are interested in knowing what is behind the whole formulation. But let's say you are just interested in a particular plant, which is what we will be doing here. So we will just use that particular plant and we fish out, we look directly for the components inside the plant, and we go on and try and predict and look for the targets. So it can be from a whole formulation, so a different set of different plants all together to find out the effect of how do you call it, of a formulation, or just a particular plant you are interested in, and you can directly use that plant. So in our case, we will be using the plant that you suggest. Let's see if the plant, we will find the plant in our database. If you find, thank God, we continue to use it. So macaranga barteri.
So in this case, what database are we using for the plants?
Yes, sure. So we'll be using phytochemicals, this thing, phytochemical interactions database. I will put
Please share your
the
screen.
I will uh,
Please, can you share your screen so we can
yeah,
see it how you're doing it?
I'm not doing it yet. That's why I will show the screen.
All right.
Yeah, so the
Then,
database, I will put
yeah.
the how do you call it, the link. Yeah, and you will also see it when I will start sharing. So the database that we will be using, let's try this. Google.com phytochemical phytoche- phytochemical phytochemical interactions database. Phytochemical interaction database. Phytochemical interaction database. Okay, so this database here. So this is the database we will use and try to ask them to give us the components of our plant of interest. Where is the chart? So this is the link. I'll send the link to in the chat. You can find it there. So in this database now, we will input our plant of interest species. You can just come on species and search for species. So you are offered to search by name, Macaranga battery. So we have this is the result that the database is giving us on Macaranga battery. And before I forget, I know I said it before, but let me emphasize on it again. So I was saying that in this database, the database will only give us the different components that it has in the database. But maybe there has been another component, other components that has been discovered. Sorry, are you now seeing my screen?
Yes, we
Yes,
can
we
see your
can.
screen.
Okay, thank you. So if there are other, there might be other components of the plant that is not accessible in the database. Our work now is to go and search the literature, the literature. So what are
Sorry,
the
so we are limited by the database, but we can search literature, right?
Yes, if we want to put it like that. Like
Okay.
what we are saying is we don't know if we have
Mm,
everything, every compound that is accessible for the plant in the database. We don't know.
mhm.
So that's why we want to go on and search the literature and
Okay.
add it up. In fact,
So
generally you will not.
we can add it to the database, right?
Sorry, you said.
Can we add our literature search to the database? I mean, can we like add to the database aside what has been there?
Okay,
Do you
if I
understand my
understand your
question?
question, my answer will be when I said search for the literature, for example, there is this another database, PubMed, for literature search.
Mhm.
Do I answer the question?
Yes. What
So
I'm saying
that's
is after obtaining our our data maybe from um, PubMed,
yes.
now can we update it here with this PCIDB?
Okay. It's not for you. Sorry. It's not for you to update this database. I mean,
Okay.
I mean, we are not the owner of the database, and the database
Okay. Okay.
doesn't give us that opportunity,
That access. Okay.
that access. Yeah. So what you are just interested in picking the how do you call it, the compound that you find on this database,
Sure.
picking the compound you can find in other databases and even in the literature, and make up your own database of compounds of your plant. Please, do you
Yeah.
follow?
Understood. Yeah.
uh
Understood.
So, by the way, actually, generally, you will not also use only one database for this search. For example, there are other databases that, if you are interested in, you can also search those databases. So the idea is just to make sure that as much as possible, you get all the components of the plant, all the components available as much as possible, so that you don't go by without any component. Maybe by doing so, that's the main component that will be giving you good results thereafter. So that's what. So okay, in our this database now, we will just click on this, on the plant. Okay, sorry, let me remember something also. uh we know that plants have synonyms. Macaranga battery, for example. Me, I don't know the synonym, but we can go in the plant list and search for the synonym. The plant list. So we go here and in the search, uh, we will just enter the Macaranga battery and try and see if we have some other synonyms, because this database that we've just the PCIDB database is what you give the database that the database will bring to you. So suppose that this one, the Macaranga battery, has other synonyms, and in the database you have those synonyms. You see, for example, here we have different species of the Macaranga. This is because I just input the genus. Now, if in the plant list I find out the synonyms of Macaranga, okay, so here the Macaranga battery is the accepted name, correct? Now, these are different synonyms that we have for this plant. So to make sure that our plants that we are using for our work uh, still in the ideology of making sure that we have all the components that is available, we want to put these synonyms in that database to see whether the database consider two synonyms as different species. Please, do you get that? Oh, sorry. So I copy, for example, these synonyms here, and I will try and put it in the database here. Macaranga Fidelity, something like that. Or I could just check it here. So it's saying that zero result. So it doesn't know that
Yannick,
species.
sorry, I can't see your screen again. Oh,
Sorry, you said?
I can't see your screen again. Sorry,
Oh,
I can't see your screen again.
okay. Are you seeing it now?
Yes, yes, I can see it now. Thank you.
So you can see the PCIDB database interface.
Yes, sir.
Okay, thank you. So okay, let me just take it back. So I just copied this the synonym here. I hope at least you hear the explanation why we are doing the synonym thing.
Yes, sir. Yes.
So so we just copy in the plant list, and we copy the synonyms, and we paste in the database. Oh la la. So we copy in this database, and for this synonym, the database is returning zero result. So we can try for the uh, other synonyms. Lancifolia. So even the Macaranga lancifolia also is returning zero result. But I'm not convinced about this. Let me see something. Okay, so we will now try the other synonym. Okay, so in our database, this database is recognizing only the Macaranga battery as the species that we are interested. So we are good to go. So battery. So now this is our Macaranga battery that the how do you call it? The database is giving us. So what we are interested in is the metabolite list. Here you can see here. Sorry, I was not able to find out how to make this pointer like be guiding you better. But in the video, the app that the software that I'm using to screen, I mean to record the screen, uh, is actually giving the opportunity to follow the cursor very well. And by the moment you get the recording, it will be easier for you to follow. Thank you. So we are interested in the metabolite list here. So this is what we will click on. And by the moment we click it, it will just pop it up. And here we have the different metabolites that we can find in Macaranga bacteria, and that this database is able to give us. So here the database is giving us four, if you see the name here. So these four uh, component: gallic acid, scopolamine, methyl gallate, gallogen, or ellagic acid. So those four compounds. What I want to do now is to create Excel file for that, and I will be copying them. Scopolamine, methyl gallate. When they write, for example, here, when they write methyl gallate slash methyl 3,4, those are synonyms too. I believe so, yeah. So generally what I do is I copy everything plus the synonyms, because you don't know where you want to put one particular name in a particular database, and the database doesn't know that name, and maybe it's the synonym that the database knows. I get you get what I'm trying to say. So methyl gallate. So our last compound from the database here is gallogen. Gallogen. Or ellagic acid. I think I will also give you maybe link or just the name of other databases that people also used to use. In fact, how do you call it? The papers that I sent on request of Zainab last time in the group. So if when you will go through the paper, you will see that there are other databases that can be used, and you just go on those databases and by trying trying how do you call it, trial or errors until you will know how to actually use it. It's generally not a big deal, not complicated. So 1, 2, 3, 4, we now have our 4 metabolites here. So those are the metabolites that we find in this database for our Macaranga battery. So as I said, okay, I will just show this the PubMed database. I guess you guys knows it too. PubMed, we will not do the search from the literature. We will not do it. Here we are just for the purpose of learning and knowing and having an idea of how the thing is done. Because, for example, this maybe you will have from the literature, you will have a large amount of paper and a large amount of paper, and you will need to be going through one by one and checking the abstract and the title, the abstract, having an idea of whether you can find whether the paper is dealing with the compounds or I mean when you will go through you will go into the paper, can you find the compounds or what you really want. For some papers you will need to go through the whole paper before fishing out the compounds of the plants and etc etc. So I think we will not do it here, but at least you have an idea, and this is the PubMed database for if in case there are some people that don't know the database, I will just paste the link here in the chat, so you have the link in the chat there. This is just a result of a bad connection right now. So come on, okay, so this is the pubmed.ncbi etc. You have the link in the chat, so we will just put in macaranga battery. So we just put it Macaranga battery here. The PubMed is bringing up 7 results. So these 7 results, these are the 7 papers that are available in the PubMed that are talking about our plant of interest. So what when I now search now like this, what the next thing for me is to take these papers one by one by just clicking on them. Those I can get directly. Uh, those are those that are free. You can access freely. You can get them directly. Those are that you cannot get here. So you find any way, any means by which you can you can just get it. Generally, you will want to go on SCI Hub. So this is the interface of XCI hub. So SCI hub has a large range of papers, even some of most of the ones that are not freely available. You can find it on SCI hub. I think I will copy this and send in the chat as well, for in case some people don't know. So SCI hub, generally you will find, yeah, and still, as we know, systems have their own limitations. So SCI hub will, yeah, give you a large amount of paper, but sometimes there are some paper that SCI hub also don't know how to. So if you have an institutional, if you are yeah, your institution is how do you call it, subscribe to particular journals and all those things of that you need, and you can just go through the means of using the institutional this thing. In all, what you can do to have the whole paper, the full paper, you try your best and do it. So that's how you find out different paper of on your plant of interest, and you try and read them, go through them, and fish out, if necessary, if there is the compounds of interest. Okay, so now so by the moment you will now be going through those papers, and you are having the compounds, you can be writing them down, adding them to your database that you are composing. So compound A, I find compound A, I will write it down. Compound B, I will write it down. Compound C, etc., etc., until I have all that, as much as possible, all that is available. So from now, we reach we have been able to fish out the different metabolites of our plant of interest. The next thing, the next thing now is to predict. The next thing will be to predict the targets, yeah, the targets of these different compounds. So that's what we will be doing in the next few minutes. So we will still take our break of less than 1 minute, and we come right back. Thank you.
Recording. Recording in progress.
So I will just share the screen immediately. So we stopped on finding the different metabolites in our plant of interest. Now, what we want to do now is to find out, to predict the targets, the genes of these compounds. Hey God, of these compounds. Okay, we will try we will try what we can do, because they just got light, and I just have 33% here, but I trust that we can do something. So what we want to do is to fish out the targets that to predict the targets of these compounds, and we will be using some databases. So the first thing will be PubChem. If you did not hear about PubChem before, we will find it now. We can go on Google. We just tell Google that we want PubChem database, and we bring the PubChem. This is the link to the PubChem. We are going on PubChem to actually find what is called the smiles. Let me write it down. The smiles of our compound. Smiles as like we smile. So the smiles of our compound. Because the database that will help us to predict the targets needs those smiles, to actually draw or bring out the structure of our compound of interest. And because it's based on the structure of the compound that the prediction will be made in that database. So first of all, we need PubChem, and the second thing we need will be the Swiss target. Okay, let me send the PubChem link. This is the PubChem link. I'll send in a chat. And now we want the Swiss target prediction. So this is the database, the website of the Swiss target prediction. I will also send it in the chat, the link in the chat. So this is the interface of the Swiss target prediction database. And here we will be inputting the smile. You can read here. I will just cover it here. You can read here. Paste a smile in this box or draw a molecule. So it's either we know the smiles and we paste it here, and then we say, please predict the target, or we don't know it, and the Marvin interface that is incorporated in this database, we will just draw the structure there in case you don't have the smiles. So, and you don't have the smile and you know the structure, so you can draw the structure here, and you can also use the drawing to just predict the target. So this is how the interface of this database, yeah, is presented. So the first thing first, we come back to this is the interface of the PubChem. So our compound is what? The first compound we have is gallic acid. So we will just tell PubChem we want to have gallic acid. Oh la la. Gallic acid, come fast. Oh. Okay, gallic acid is saying best match. So usually I will just pick the best match, but at least making sure that I have gallic acid inside all this. So I will just click on this gallic acid link here, and it will lead me to the PubChem informations, all this thing about the gallic acid. You can check all the information that are available on a particular uh, for a particular compound. You can check it by your own, but for now what we are interested in is the structure, is the smile number of this particular gallic acid. So the smile number, by scrolling down you will see it very soon. This is it. Canonical smiles. Canonical smiles. This is it here. Canonical smile. And this is the canonical smile of the gallic acid. This is what we want. So sometimes for some compound, you will see canonical smile, and you will still see I think isomeric smiles. So for the purpose of what we are doing, it will give you the same thing actually. Either you take the canonical smiles or the isomeric smile to put inside Swiss target prediction database. It will give you, will predict the same targets for you. So we will just copy. I highlight it and I just copy it and I will paste here. I will paste it here. By the moment you paste, you will now see that it will draw the molecule at the right in the Maven JavaScript this thing software, and the predict target in red here, the button for the predict target also will pop up, will come, and then you will just click on the predict target. It says your job was submitted, etc. So it's running, and we will wait patiently for what it will bring for us. So our Swiss target has predicted the targets for our gallic acids. Here you can say it's showing 15 intries. For now, it's just showing 15 intries. If you want it to show all intries, and these targets actually will bring you in total 100 targets. That's what this particular database does. So you can just tell it, the database, show me all the intries. So it will give you all. And generally, you will see down here, is saying showing uh, showing 1 to 100 intries. So it's always give you 100 intries. And this chart, this pie chart here is actually showing the classes of the target of your compound. So I can just click on this so that you will see it largely. And it's saying that 80% of the targets that we have are liars or liases, and 13.3% are enzymes, and the other percentage is for transferases. But this right here is just for prediction of the top 15 targets. So if you want to see the percentage of different classes for all, you will just click on all, and it will bring another pie chart for you. By just clicking it, you will see, and you will have what you have here. If you are interested in presenting this in your work, then you can use it. Otherwise, if this is not really what you want, you just keep it. So what we are really interested in here is just the targets that we want. So from here, we now want to download the target, and you will see export results here. Where you see export results, the CSV, you can download in a CSV format, or the X here is the Excel sheet format. This is the PDF format, and this if you want to print. So I usually download in Excel, so I will just click on the Excel, and you can see here it has downloaded uh, Swiss target prediction 39.xlsx. So that's the target for our compound. We just open this file, and then later we just save it. Please, are you following me? I hope you are seeing the screen, everything I'm doing.
Yes, sir.
Okay, thank you. So these are hmm, the compound, the targets of garlic acid that is predicted by Swiss target database. So this is all we have here. We have the name, the target name here, and we have the common name, the gene name, and we have what is called UniProt ID. We have UniProt, ChemBL. They are all other chemical databases. Yeah, and each chemical databases has its own way of nomenclature of every and each chemical compound. Even the IDB that we used right now, you will see that when we was on the interface. Okay, let me see if he is still here. He's not here. Yeah, so if you come here, let's just go back small and let me see. Yeah, by name. Okay, so it just brought me metabol. But what I want to show you is just that this is just to show you that every database has its own way of nomenclature. So you will see that here this KNAP SAC ID is what is used for this particular PCIDB database. So for example, for Macaranga flavanone B, Macaranga flavanone B, for example. So this is its own ID in this particular database. But if you go in ChemBL database, this is its own ID here. So each and every database has its own way of nomenclature. So you will have the common names here, the UniProt ID, the ChemB ID, the target class, the probability of so this probability is just saying that here, this probability is just saying that the probability of of this target to be actually uh, uh, to really be a target for the compound that we have inserted. So that's just the meaning. But me, I don't focus on the probability. I use the whole 100 targets for my study. So we have our this thing now. We will just let's just save
Sorry,
it. Yes.
what does the probability imply? I mean, I'm seeing that it's showing higher probability for some metabolite or for some target than for some others.
Yes.
So what does it imply?
Yeah, that's like I said right now. So it just implies that the probability of this target for a target like to really be the probability of how do you call the macromolecule to be a target for the compound. For example, when we see this, okay, the first one here is carbonic anhydrase 2. We see that the probability range is almost full compared to when we come down for squalene monooxygenase here. It's not full.
Hmm?
So it's just implying that most likely this carbonic anhydrase 2 is most likely to be a real target for our compound gallic acid than this squalene monooxide. Don't forget that all we are doing is prediction.
Okay.
Because okay, if I didn't say it in the beginning, because we need to know that the network pharmacology, okay, so is all about prediction, and usually is not finished until you test them in experimentally to confirm that yes, truly this compound can bind to this target, and this is probably the mechanism behind the effect of the whole plant and etc. I hope I get that correct. I hope you
Yes.
follow.
Yes.
So that's just what is implying.
Thank you.
Yes, thank you. So we will let's just save this one. Yeah. Okay, I see. Let's save it in our folder. Document network farm discussion. Open. So this right here is for garlic acid. I will just say sweet target prediction for garlic acid, and I'll just enter. So this is the first one. We will now do the prediction for another compound, the scopolamine. So we just copy scopolamine. We will go in PubChem, search PubChem. I just paste scopolamine. I ask it bring scopolamine for me. I will just click on scopolamine. I now have my interface for scopolamine. What I'm interested in is the canonical smiles. So I have my canonical smiles of scopolamine here. I just copy it and I come in Swiss target prediction database, and I will tell this target, this database, see, I don't want this, I clear you, and I just paste it, and I say now bring me the targets that you think uh, that you predict for my compound scopolamine. So like before, we just ask it give me all, and then I have all, and for the Excel I will just download, and I have my this thing here.
Sorry, Yannick.
Yes,
Okay, for this last one you just checked, scopolamine. There are
yes.
some of them that the probability is 0. There are some of them that has a probability of 0. Will those ones still be
Even
useful?
even the first one we did, some of them had nothing here. So that's what I was actually explaining, that all these things is prediction. So I believe that the algorithm behind this database is using the structure of the molecule that you give to the database to predict, is structure based, to predict your targets. You get right? So now it's telling us that is a prediction. It's not 100% sure. And I was saying that if you like, maybe you have a zero prediction here. And you said, me, I don't want to consider the targets that are with zero prediction here. You get, and you will not use them. But I was saying that, but me, I used to use everything that has been given by the software here. So all is about prediction. Is at the end when you have you will go in the wet lab and you have all it takes, the reagents, the facilities, and you want to now test it experimentally. And now you will now test it and find out really this is working, really this is not working. You will find out that, in fact, when you will be working yourself later, you will find we will talk about molecular docking, as we said, as I said before yesterday. We talk about molecular docking. You will even
Because
find out that
I was almost asking, there was a difference between this and molecular docking. So
The
you know, it's
molecular
structure based. Yeah,
the molecular docking now will actually give you the binding, how do you call it, the binding
stories
energy.
like
The
the affinity, binding
Thank
affinity.
you, the binding affinity. So you will use the binding energy value to see what's the binding, which one is the best affinity. So when you want now to, for example, here we cannot decide, uh, we don't know the binding affinity here, and we cannot just decide that these are the molecule I want to take into the experimental work for now. But by the moment we run the docking and we see the binding energy, and we can sort the binding in by binding energy, and see that this particular target is like they are binding better. So let me try this once experimentally. Let's say maybe it's also a cost effective related, if we can also say it like that. And in the molecular docking, actually, is it will also tell you um the, how do you call this, the binding sites between your ligand and your macromolecule. So what is binding to what, you will find out, which you cannot find out here. The different interactions, the hydrogens, bonds, and all those things, you will know them, the molecular docking will tell you. I hope I answer.
Yes, yes.
Okay,
I'm looking
so
forward to
yeah, we will,
that.
by God's grace, we will try and reach there.
Yeah.
So we were here. We just wanted to just yeah. Power outage will not help us. So
Okay, we can whatever the battery life can, you know, we can stop there for today. So at least we have reached a point.
somewhat.
Hey,
So this is the Swiss prediction for score. What's the
scopolating.
scoprolatin? Okay, scoprolatin, something like that. So we are done with this one also. So the methyl gallate, or maybe let me check this.
I want you
Please.
to try. There are, because we worked on that Makalanga, but there are even when you were checking PubMed, some of the
Uh-huh.
articles that brought they were publications. There are about three, or like three compounds that were very active for anti-cancer and antiviral: vedelianine,
But we
inostigmine.
didn't find them in
It
in
was
this
not in
database.
this PC phytochemical something database,
Exactly. Exactly.
interaction database, not there. But if you open
Article.
that article, you will find
Find
like
it there.
three or four
Okay.
compounds that were active. In fact, we
Yeah.
tested them for antiviral again, they were active.
Okay.
So,
So that's what we were saying in the beginning, that
mhm,
it's important to also check around and
literature.
multiple databases to make sure you have enough. Uh,
Mhm.
what I'm now thinking is maybe we will not predict the remaining two. We will just go on with the next stage, so that we progress fast. What do you think? At least
Yes,
we
I
know
think
how
the two examples they are
is
enough.
enough.
I mean, yeah.
So that's it. So what we now want to do is let's suppose that we had all our metabolites, even plus the one you are saying now, and we check for every target. So we will now put the targets, all the targets, because we are working in terms of the plant, but not in terms of the plant, not necessarily in terms of each and every compound for now. So we will put how do you call it, the different predicted targets together. We will remove the duplicates just like we did before, and we have the database for the targets, I mean the established database for the components of our plant. And that's where now we will now, okay, let's just do it. um this. So I will just copy this. This is for garlic acid, and if I like, I can just create how do you call it, create another file, and I will put it here, and I open the other ones. Here we just have scoprolatin. Now we copy and we copy, and in our new file that we created, I want to put it under here. So now, by just leveraging on Excel, so these are genes. By just leveraging on Excel, I will just select the whole column, and I will look for how to remove duplicate. I will say remove duplicate, and it's telling me I can tell it my data has a headers, so it will just click it, so it will not consider the genes, the head. And I will say yes, search for the duplicate. It said it finds 40 duplicates value, and this is the unique remaining. So now I know that I have no more duplicates, and this one can constitute the my database for from my database for the predicted targets for my plant. So yeah, net farm. Okay, I can I have the element, I have the plant, so I can say our plant is Macaranga MB. I can say MB target. So I now have, that means from yesterday till now, we were able to establish the predicted genes. So from 10 minutes. So from yesterday till now, we were now able to predict the genes for our ailments, our disease, which is breast cancer. And we will now, today we predicted the target. First of all, we find out the components, the metabolites of our plant. And now based on those metabolites, we went into PubChem. We find their smiles and went to a particular database that can help us to predict the targets. As I said before, and even yesterday, there are multiple databases doing the same work. So you can either choose to use more than one database for a particular work, or you can choose to use just one database as you want. As you will be going through the literature, you will find out what you prefer, and their criteria, how they are using it, and decide that this is better for me, or I prefer to use it, or I want to use different together. So today we were able to now predict the targets for our compounds. And what is next is put the compound, because we now want to find the common genes between the plant. Let's say the let's say like behind our head, what we think is this is our drug. So we find the targets that are common for our drug, and then the disease. I don't know if someone is getting why it is important.
Can you come again?
Yes, we find targets for the disease, and we find target for the plant. And we are saying that the plant, we are thinking that this is the drug. We are trying to find out a drug from that plant. So if the genes that the drugs are predicted are in fact the genes that are involved in that disease, so we are on a good path. That's why is of interest for us to find out the common genes between the disease and the common genes predicted for the disease and predicted for the plant.
Is it from my
Which
side? Network is, or is on
oh
network?
I think it is network. It's also here too.
Okay.
okay, sorry. Can you hear me now?
Yes.
Okay, so I was saying that where did you hear me where did you hear
That
me
if
to?
that aligns with the gene in the case, something.
Okay. All right, so let me just take it again. We want to find the common genes, the genes that are common for both uh, the disease and both the plant, which is supposed to be our future drug. So I guess now, I hope now you understand why it's important to just find out the common genes and continue our work with the common genes. Yeah, because
Yes.
uh, uh
I think after watching the recording, I will have a better understanding, sha, but to an extent,
all
I
right.
understand.
Oh, okay. It's important because if the disease you want to cure, you have the disease you want to cure here, you have the drug you want to cure here. The drug is supposed to act on particular sites of what is actually involved in the progression of that disease. So we found out that those genes, there are genes that are involved in the progression of the disease. And if the same genes that are involved in the progression of the disease are predicted for our drug, let's say our drug, that means we are on a good way. That's why we just want to find the common genes. So doing that, we will be using another database uh, to to draw a Venn diagram and have the common genes. Okay, I think we will stop here. We will stop here. We will stop here. We will stop here and we will continue on Thursday because this thing will not allow us to continue. So we will stop
Mm.
here and we will continue on Thursday. Thank you very much for coming on board today. And we hope that God will grant us grace as we are continuing until we understand something about what we are doing. Thank you.